Hello, hello, Year 11 Chem. Today we're going to take a look at intermolecular forces. These are the forces that actually happen between molecules. And what these do is they affect the physical properties of many materials that are composed of small molecules. And so they can be quite interesting in how they actually affect the physical properties of some common substances like water. This is just part of finishing off Module 1 in the bonding section of the topic. And the best way to start this is to look at a series of examples with methane, water, ammonia, and hydrogen sulfide. We have the Lewis structures pictured on the screen, and they're arranged in such a way to give some idea of the three-dimensional structure of each of these molecules. Although if we take a look at the next slide, we can actually see a little bit of a better comparison where you can see the tetrahedral, bent, pyramidal shape of each molecule. All right. Now, one of the things you'll notice here, the molecular weight is increasing from left to right as you go from methane all the way across to hydrogen sulfide. But if we come down to their physical properties, the melting point and boiling point, which is the bottom row, you'll actually see that one of these molecules is not like the others. Water has an exceptionally high melting point and boiling point. And to be honest with you, so does ammonia, all right, in comparison. That means there's something else going on here. So let's actually look at that graphically. So if we look at the melting and boiling point of these molecules, if we were looking at hydrocarbons, as the molar weight, molecular weight, increases, what you would be expecting is the melting point and boiling point are going to increase in a linear line. But we're not looking at hydrocarbons, we're looking at a mixture of different small molecules. And what we can actually see is that the melting point of water in particular is really high. Ammonia, unusually high as well. Okay, they're so high that there has to be something else going on there. So let's get on to explaining what that something else is. All right, so there's some things we need to know going into this, and that is about intermolecular forces. So just some language. Intermolecular means the bonds between molecules. So, and intramolecular means the bonds that are within a molecule. So when we talk about a covalent or an ionic bond, we're talking about the bond inside a molecule or the bond inside a compound. In that case, we're talking about properties related to the material's bonds itself. When we're talking about intramolecular forces, we're talking about properties that are that affect how the molecule interacts with other molecules. Now, there are three types of intermolecular forces. There are dispersion forces, which everything has. All right, and these are caused by the formation of what's called temporary dipoles. Now, a dipole is uneven charge, and they happen naturally as electrons move around molecules. You can think of it as like if you were to hit pause, and as the electrons are buzzing around the nuclei of the atoms, every so often there's going to be more on the left than the right, for example, and so you'll have a slightly positive or slightly negative side of the molecule. This is one of the things that causes random movement, all right, of particles. All right, one of them, not the only one. All right, but there are two other types of intermolecular forces that are of interest. There are dipole forces. Now, these happen in the presence of polar bonds. So remember that covalent bonds, if we look at my hands here in the little picture in the top right, kind of if you think of the individual atoms as having two hands out, they're holding the two electrons. A polar covalent bond is when the sharing is not equal. Okay, so you can kind of think of it like tug of war. You're going to have one atom that is far more electronegative than the other one, and it's going to be pulling those pair of electrons towards it. All right, when you have a bond like that, you end up with a partial positive and partial negative side to the bond. And they tend to be much stronger than dispersion forces, and they affect how these particles interact with other particles. And there's a special case of dipole interactions called hydrogen bonds, which only are present when hydrogen is directly connected to an oxygen, a nitrogen, or a fluorine. Case in point, our water and our ammonia have hydrogen connected to oxygen and nitrogen. Oxygen, nitrogen, and fluorine are the three most electronegative elements, and these are the strongest intermolecular forces. Now, they're still far weaker than covalent bonds, but they are strong enough that you can see them really easily in the properties of small molecules, particularly ones like water. Now, getting into this, if we look at dipole-dipole interactions, so just take note, we previously defined electronegativity as the tendency of an atom to attract electrons to itself, with fluorine notably being the most electronegative atom. When you have a covalent bond where you have unequal sharing of those electrons, you end up with a partially negative charge towards the more electronegative atom that is part of the bond, and a partially positive charge towards the less electronegative atom. All that means is that our two electrons sitting in that bond are sitting closer to the electronegative atom. So if we take a look at the example down the bottom, we have hydrogen chloride, or which most people will be familiar with as hydrochloric acid. But if you actually just have hydrogen chloride by itself, it's actually a gas. All right, it reacts with water to form hydrochloric acid. Now, part of the reason why that's a reactive molecule is because that covalent bond is polar enough that it's pretty easy to chip that hydrogen off. And what actually happens is, again, that unequal sharing. Think of it like tug of war. All right, the chlorine is just far bigger and stronger than the hydrogen when it comes to grabbing a hold of electrons, so it pulls them towards it. All right, this means that the chlorine side of the molecule, slightly negative, the hydrogen side, slightly positive. Now notice we use a bit of a weird symbol. It's a Greek letter called delta down there next to the positive and negative sign. Now, if we think about there being polar bonds, all right, one of the things that you need to be mindful of is that means there can be molecules that have a overall positive and negative end. All right. However, some molecules are symmetrical, and through being symmetrical, they won't have a dipole. Okay, there's an example of one on this slide just here, where we have beryllium fluoride. Okay, because it forms a linear molecule, and that molecule is symmetrical, the polar bonds balance each other out, and so it doesn't have an overall net dipole, and those polar bonds don't affect the physical properties of that molecule. Now, what you're going to do next is you're going to pause this video, hit pause, and have a go at the challenge questions on the video. Oh wait, don't worry. Let's carry on. Okay, and so just looking at these challenge questions just here, we've drawn out the molecular shape of water, ammonia, and beryllium trifluoride. We've labeled the partial charges on each of them. Okay, and we've worked out the direction of the dipoles from positive to negative. And that gives us an idea of the net direction. Think of it kind of like a vector for the physics students, all right, for the direction of the dipole. We can take a look at these in a future Zoom lesson. So when you have molecules with dipoles, because you have an overall positive and negative side of the molecule, you end up with some sort of attraction between different sides of the molecule. Okay, this affects the physical properties because you have an extra force holding those molecules together. All right, now in the case of hydrogen bonding, it's much, much stronger than dipole-dipole bonding. All right, that's quite possibly likely because of the point that hydrogen itself just doesn't have much ability to hold onto those electrons, and so it has a very large difference in charge across that bond. Now, when we draw this, what we usually do is a dashed line between them, kind of like what is shown on the picture on the right-hand side just here. Now, usually that means that we have the negative oxygen in the case of water and the negative nitrogen in the case of ammonia, and I mean partially negative, not a true negative like you would have with an ionic bond, is attracted towards the slightly positively charged hydrogens on the other end of the molecules. And because we have that pretty strong dipole in the case of hydrogen bonding, attracting those molecules together, there's an extra force holding those particles together when we add additional heat to them. All right, so it takes more energy to force them apart. All right, you can kind of think of it like elastic bands holding the particles together to actually get them to spread out further as you heat the matter up and go from liquid to gas, or from solid to liquid. You need to put extra energy in, hence why they have a higher melting and boiling point. Okay, so it's pretty straightforward now why we can see what's going on here. The reason why ammonia and water have relatively high melting and boiling points is because they have an additional force holding their particles together, whereas methane and hydrogen sulfide don't have the hydrogen bonding. That means that everything here, all right, methane, ammonia, water, hydrogen sulfide, they all have dispersion forces. All right, there are dipoles, dipole-dipole interactions for all of them but methane. But there is only hydrogen bonds for ammonia and water. And that's where, because they're far stronger than dipole interactions, that's where we're seeing that significant change in melting point and boiling point. Being able to recognize molecules that may have hydrogen bonds is a really important skill year 11, because whenever you are asked a question in year 12 about the physical properties, they're usually around the boiling point of a hydrocarbon. It's usually a hydrocarbon that has an OH group in it, which is going to have hydrogen bonding. It's pretty much always hydrogen bonding or a lack of hydrogen bonding that is affecting the properties of a molecule. All right, something to keep in mind. Okay, that wraps us up for our video. Year 11, thank you for watching the video. Let's get on with the lesson. Bye.